Hi everyone, thank you for the introduction. My name is Ashley Edwards and I'm a research scientist at Uber AI Labs. The focus of this talk will be on an imitation from observation approach that I worked on during my PhD at Georgia Tech. So imitation learning is an approach for learning from states and actions from expert demonstrations. For example, maybe I want to teach a robot to play boxing by showing it how to move all the different positions on a joystick. But the world consists of a lot of data that would be really interesting to learn from that doesn't involve me having to show the agent how to do every single possible thing. So let's say, for example, I wanted to actually learn to imitate by looking for a video of someone playing the boxing game online. In these sorts of settings, I don't actually have access to actions. And so if we're interested in imitating when we don't have access to actions, we can use an approach known as imitation from observation. So this is an approach that allows us to learn from state observations only. And there are a couple of different ways that we can do this. One of them is to learn a dynamics model. So given a video, we can act around in the agent's environment and have it take different actions and try to infer what the dynamics model was. And then once we learn that dynamics model, we can try to infer which actions were taken in our video. Another thing that we can do is learn a reward function. So we can learn a goal detector that says, is the agent at the goal? Or we can learn some other sorts of reward functions. And then we can train reinforcement learning using those different kinds of approaches. The problem with both of these techniques is that it typically requires a lot of environment interactions. So if we want to learn a model of our dynamics, that's going to require us to take a lot of different actions in our environment. And if we want to train a reinforcement learning agent, again, we're going to have to act around in our environment a lot in order to learn a value function. So during this talk, I'm going to talk about how we can learn value functions rather than reward functions directly from observation. And then I'm going to talk about how we can learn policies without actually having to learn a value function at all. So the first work that I'm going to talk about is perceptual values from observation. So in this approach, given a video or a sequence of state observations, we're going to try to learn a value function. And then using that value function, we're going to train a reinforcement learning agent. But the important thing to note is now we're learning a value instead of a reward function, which will give us more of a shaping signal in order to train our agent more quickly. So let's assume we have some sort of demonstration like this. Let's say we have a robot and we want it to get to the end of the hallway. So how can we define a value function for something like this? And remember, again, we don't have access to the actions, the reward signal, or anything like that. And typically when you want to learn a value function, those are the things that you need to have in order to learn that value function. Well, one thing that we do know when we get a demonstration is that when we get to the end of a task, that's basically like what we wanted the agent to solve. So if I have a video, we can sort of assume, unless our demonstrator is sort of terrible, that the task has been completed within that video. So we might say, okay, well, I have my video. Let's give my agent a reward of 1 when it reaches the end of that video. So we can say when it's in that state, it should get a reward of 1. And again, we could do something like reinforcement learning just from a signal, but in a difficult task, it might be hard to train an agent using that sort of signal. So one other thing that we can say is, okay, well, what should I get, or what kind of value should I give in the beginning of a task? So one thing that we do know is how we can actually define values. So our value function is described as the sum of discounted rewards over time. And because we know that at the end of the video, the agent should get a reward of 1, I know basically how far away I am from the end of the video. I'm basically t steps away. And actually, does this work? It doesn't. I would point at things. Sorry, I won't point. Basically, we know that we're t steps away. So we can give our agent a value of gamma to the t minus 1. And this is basically coming from our sum of rewards that says my value is going to be my reward plus my discounted reward plus my next discounted reward, etc. Because we're getting a bunch of 0 rewards until we get to the end, we know we can define our reward function or our value function to be gamma to the t minus 1. Oh. Oh, wow, this is thank you. I feel powerful right now. Okay, awesome. Right, and so now if we want to define our values for any intermediate step, or more generally, when we're at the tth step, we can basically say that my value function is going to be gamma to the big T, which is the length of my video, minus t, which is my current position, which is just saying my value is going to be based on how far away I am from the goal. Okay, so there are a couple of things that we can do once we learn this value function. The first thing, so if you do reinforcement learning, you're probably familiar with this formula, which is just basically saying, what is my value for being in a state, assuming that I take a particular action. One problem with this is that it requires us to do something called bootstrapping. And so when we're making these estimates, we have to use our current estimate in order to make the updates, which can make things difficult. But because I've actually learned a value function, I already know what this quantity here is. And so I can just replace that bootstrapping step with my learned value function. One other thing that I should point out is that because we're learning, because we have a sparse reward problem, which means that we only assume that the reward is 1 once we reach the goal, we can just basically get rid of that here, and this will become our update rule, and we can use this to train reinforcement learning problems. One other thing that we can do is use that value function to replace our reward signal. And so this is something known as a potential-based reward function, but basically what this is saying is that we can just plug in my value function as my reward signal and then do regular reinforcement learning with this. Okay, so we tried this out in a couple of different environments. The first environment is something called the maze environment, where you have a blue object that needs to navigate to a green object. And we're basically, in these first experiments, I'm just going to talk about what do the values that I learned look like. And then in the next experiments, I'll talk about can these values be used to train reinforcement learning agents. So I trained the value function in 1,000 demonstrations, and I tried it out on different sized mazes, and I wanted to basically see, am I able to generalize to a new maze that I haven't seen before? And so this is what the results look like. So you can see basically here, if you look around where the goal is, the values of the agent in different states decrease as you get further and further away from the goal. And so that's pretty much the sort of thing that we want to see when we're learning a value function. Okay, the next experiment was in this liquid pouring task. So in this task, you basically have humans pouring different kinds of liquids in different settings. So you can see basically like you're pouring like milk and Coke or whatever, and you have a lot of different cluttered environments. And again, what we wanted to see is if we trained in these environments, would we be able to predict the values of being in completely unseen environments before? So in this case, we trained with only 10 demonstrations, and we evaluated in a different setting. So this is what the results look like. So you can see here, this is time, and this is the value as you go further along in the video. And you can basically see that our values increase over time, which is, again, the sort of thing that you want to see in a value function. And the final results that we did for this problem was training reinforcement learning agents. And so in this task, we evaluated within the coin run environment. And so in this task, you have an agent that needs to get to a coin. This is a platform game. And this environment is procedurally generated. So basically, you have like randomly generated backgrounds. The color of the agent changes. And again, we're interested in, are we able to generalize if we learn a value function, again, from only videos of someone performing tasks in these environments, will we be able to predict the value in an unseen environment? And now we're going to use those values to actually train reinforcement learning agents. So this is what the results look like here. Basically on the x-axis, we have our episodes, and this is our reward over time. And we basically just compare it against the standard reward function, which just gives the agent a reward of 1 once it reaches the coin. And you can see that we're able to learn much more quickly using this approach than using a standard reward function. And the videos on the right are just showing the agent actually reaching the goal with this method. Okay, so in summary, I've shown that values can be learned directly from observation, and that these values can be used to train reinforcement learning agents. But if you think about how we solve tasks, we don't usually have to learn the task from scratch once we've actually observed someone solving it for us. For example, if we are watching our friend play a video game that we've never played before, we can watch our friend to figure out what sort of actions we can take, like what sort of monsters or whatever happens in video games I should avoid, and that sort of thing. And once I watch them play, all I have to do is pick up the game controller, figure out how to map the controls to the sorts of things that I've seen in the world, and after that I can just basically play the game. So the idea behind this next work that I'm going to talk about, which is imitating latent policies from observation, is that what I'm going to do is first, from a sequence of observations, again, this is learning from videos, I'm going to learn something called a latent policy. So I don't have actions, so I'm going to try to figure out what latent actions look like. And then once I do that, I'm going to take a few steps in my environment to try to map this latent action representation to the real actions that I can take in the world. Okay, so imagine that I have a demonstration from a video, and I have a state like this. So there might be different transitions that I see, but I don't necessarily know what the names of them are. I just know that they look different from each other. So this is what we're defining to be a latent action. So these are things that have caused my transition to occur in my data. So these latent actions, again, can refer to the real actions that I can take in the world, but they can also be some other sort of transition that might occur that I haven't necessarily modeled. For example, maybe like my agent can bump into the wall. So that might not be an action that I can really take, but it's something that I observe in my demonstration. So what I'm going to try to do is learn a latent policy, which tells me what is the probability of taking each of these different latent actions in the world. So the first step that I'm going to do is, given a sequence of observations, try to learn this latent policy. So I have here a neural network that's trying to learn this. So given a state, what it tries to do is predict the next state given one of my latent actions. And I should point out that these latent actions aren't actually learned. It's a hyperparameter that I assume that I know. So maybe I can start off, let's say I have k actions. I'll say I have k latent actions. So given one of my latent actions in my state, I try to predict the next state. And then what I'm also going to try to do is predict what is the probability of each of these latent actions occurring, and that's what I'm calling my latent policy. Okay, so let's say I have a demonstration shown here. What I'm first going to do is try to learn a generative model that tries to predict each of these next states. So this is basically showing all of the different transitions that my latent model might try to predict. And so in order to train this, what I'm going to do is I'm going to try to find, out of all of my different generated next states, I'm going to try to find the state that looks the most like the state that I've actually observed. So here I have my state and my next state. I'm going to pick the prediction that looks the most like this next state. And then what I'm going to do is I'm going to try to minimize the distance between my predicted next states and my generated next state. And what this allows me to do is predict all of the different kinds of transitions that I can see. And basically it allows it to learn basically the latent actions that we can have. So it's trying to predict things like moving to the right and jumping and that sort of thing. But what we really care about is what is the probability of taking each of these latent actions, because that is what my policy is going to be. And so let's imagine that in my demonstration set, I have different probabilities of each of these transitions occurring. So when I'm in this state, let's say I have a probability of 0.5 to move to the right, probability of 0.5 jumping in the air, and probability of 0 for staying still. So if I were to try to guess what the next state would look like given only my state, the best thing I can do is basically average between these two states that I've observed in my data. And so that's basically exactly what our latent policy is going to try to do. So given a state, it's going to try to give a probability of each of these different transitions occurring, such that if I take the average of these things, they end up looking like the state that I would expect to see in my data. Right? Okay. Okay, so more formally what this means is what I'm going to try to predict is the expectation, so the expected next state of my, the expected next state given my current state under this latent policy. And in order to learn this, all I have to do is multiply each of my predicted next states times the probability of that state occurring. That gives me my expected next state. So that's what's happening right here. And then I can basically try to minimize the distance between my current state that occurs in my data and my predicted next state. All right. So after I learn that, what I have to figure out how to do is correspond these different latent actions to the real actions that I can take in the world. So again, I'm going to learn a network, but this step here is going to be where I'm actually taking actions in the environment. The previous step was only learned from the videos. So what I do is, given my state, what I try to learn is the probability that my real-world action corresponds to my latent action. So I'm going to try to relabel my latent actions to the real actions that I can take in the world. Okay, so now we assume that we have we've interacted with the environment. So let's say I'm in a state, I take an action, and I end up in the next state. So now what I'm going to try to do is correspond these real actions that I've taken in the world. Remember, again, I'm actually interacting with my environment now. I'm going to try to correspond these to my latent actions. So now what I can do is again, try to find, given a state, if I make a prediction, which of my predicted next states looks the most like the state that I actually observed in my transition. And so what I need to do is basically try to minimize the distance between or find the latent action that minimizes the distance between my predicted next state and the actual next state that I observe in my data. And then once I predict that, I can just try to relabel my action to be the latent action that occurred. And so I can set that to 1 and set everything else to be 0 and try to minimize, again, the difference between those things. All right, so we tried these out in a couple of different environments. The first one is a classic control environment. So this is cart pull, where an agent needs to learn to balance a pull. And we trained ILPO, so that's the acronym, I don't know if I've said it, but imitating latent policies from observation with 5,000 or 50,000 samples. And we compared it against an approach known as behavioral cloning from observation. So this is an imitation from observation approach, which first learns a dynamics model within the agent's environment. So given a state and next state, it tries to predict which action was taken. And once it learns that, it uses that action to relabel the video that it saw. So it says, okay, in my video, it was in that state, and then the next state, I know which action was taken, and that's how basically it learns what actions were taken. And the problem with this, again, is that it has to learn a dynamics model from the environment, which can take a lot of environment interactions. The next environment that we tried this in was Acrobat, where you have this thing trying to swing to the top of the screen, or this line, I guess. And again, it basically is trying to figure out which actions to take by applying different forces to its joint. And we, again, compared against behavioral cloning from observation. And finally, we tried this in something called mountain car, where you have an agent just has to learn how to drive a car up to the top of a mountain by swinging itself back and forth until it gains enough momentum. So here are the results here. So on the x-axis, we have our environment interactions. On the y-axis, we have our reward. And here in blue is behavioral cloning from observation, and our approach is in purple. And you can see that we're able to learn much more quickly with fewer environment interactions with that approach, because again, that approach has to learn the dynamics within the agent's environment, whereas we are learning our policy offline and then just taking a few steps in the environment to figure out how to map our actions to our latent actions. We also tried this in an environment, the coin run environment again, except now we're evaluating within a single environment instead of trying to model or test the generalization of this approach. And again, we had compared against behavioral cloning from observation. And so here are the results here. So we tried it out in a couple versions of that environment. The first one was a very simple one where the coin was really close. But even here, you can see that we're able to do better than behavioral cloning from observation. And then we also tried this in a more difficult version of the task where the agent needs to avoid this pit here in order to get to the coin. And we're able to do much better. And the reason, again, is that we're learning our policy offline first and then just taking a few steps to map. And the other thing to point out is that this is a higher dimensional problem, and so it's definitely much more difficult to learn dynamics models in this setting. So it will require more environment interactions in order for that to happen. So that's another reason why our approach might have ended up doing much better in this setting. And so you can see here, after just 200 steps, our approach was able to solve the task, and this is just it playing the game. Okay. So in summary, I've shown that values and policies can be learned from observation, that these can be used to train agents to imitate, but future work would entail, I think the thing that I'm actually the most excited about actually is trying to train agents to learn across environments rather than having them learn only from the same environment. And there are definitely approaches that have worked on in this area for learning to train like robots from humans and that sort of thing. So I think the future work would involve trying to do this in a more sample-efficient manner, maybe using the types of approaches that I talked before. Okay, and that's it. Thanks. Questions, I guess.
Hi, fun talk. And so I was thinking about this book I read as you were talking called The Inner Game of Tennis. And
sorry, can you repeat that? Or
the book is called The Inner Game of Tennis.
Oh, okay.
All right. And what it's trying to say is, you know, there are a couple of schools of thought on feedback. One school of thought says negative feedback is not good. Try to do positive feedback. And this book makes a yet third argument. It says you don't need a coach. You just need to have like your sort of the lizard brain or the physical plan to do the job. So I guess what I'm wondering about is this. I think there are a couple of things. One is, what is, you know, reinforcement learning feels like a kind of thing where maybe feedback is negative that comes our way, and we say, don't do that, go fix it. Have you thought about what positive feedback would look like in the context of reinforcement learning?
Yeah.
And then related, your learning from observation feels like what the inner game of tennis is actually telling to do, so that is interesting.
Yeah, good question. So actually, typically, or often in reinforcement learning problems, you actually do give the agent positive feedback. So many tasks give you a positive reward if you're able to solve a task, and it's definitely true that if you give it negative rewards, it actually usually just ends up doing nothing to avoid those negative rewards. So I think for the most part, positive signals have been used in the field. And I guess your second question was, actually, can you repeat it? Sorry.
So I think what is, like, you know, the actor-critic model is like the reward is something extraneous that comes your way, but this observation is almost something you have control over. I don't know. It's, I think there is some philosophical thing that's going on. Anyhow, take a look at that book. I think you'll enjoy it.
Okay, yeah, thank you.